All right, so we left off here yesterday talking about the domain and range of the cosine function and the sine functions. All right, so now we have our first example, finding all the t values. So state all values of t for which sine t is -1. So when I think about that, this is saying that when my y value is -1, what are my different x values? Come on. Okay, so this is my y value that we're looking at here. So when y equals -1, what x values is that true for? So the easiest way to do would be to plot this. Now I know for my unit circle that at 3 pi over 2, so the sine of 3 pi over 2 is equal to -1, right? But that's not the only time, because if I look at my actual sine function as it goes through multiple periods, here at 3 pi over 2, that's what this one would be, it's at -1. But it's also at -1 out here, it's at -1 back here, and it's at -1 here. But that doesn't stop there either. It's going to be at -1 here, and continuing on forever in both directions. The easiest way to describe when it's at -1 is to realize that it occurs once every 2 pi. So like this would be adding pi on, 1 full pi, from 3 pi to here. Then that's adding a second pi. So this cycle is from 2 pi, which we talked about that being the period of the sine and cosine functions as it is. So if I want to know everywhere that it is -1, instead of listing them all out, the easiest way to do it is to do 3 pi over 2 plus and minus k times 2 pi. And k is just a variable here. So it says that for every time I add another 2 pi on, I'm going to hit -1 again. So because this is my period, I'm just adding 2 pi on, and then k number of times, which could be any number of times. Looking at the next one, finding all t values. State all values of t for which cosine t is 1/2. So I know that cosine t is 1/2 based on my unit circle. Cosine t of 1 is 1/2 at pi over 3. So that's going to be like, there's 1/2, like right in here. I know that this is also true at -pi over 3. So let's pull the unit circle up so we can look at that. 1 second here. Okay, so if we pull up the unit circle, we can see that our cosine at 5 pi over 3 or -pi over 3 is also 1/2. So for this one, because when I look at this, it's hitting at 2 separate points each time. Like here, which is 5 pi over 3. and then here, which is going to be where our cycle starts to repeat again. So I can do pi over 3 plus or minus, and you can do k times 2 pi or 2k pi. And it's going to have to be at, you can either do negative pi over 3 plus or minus 2k pi, or you could have just done 5 pi over 3 plus or minus 2k pi. These two are the same thing, because if I look at this, if I'm starting here and I look at it as climbing the hill, okay, when I hit this point, I'm at the same exact spot climbing the hill again. So I'm starting a new period right here. So this takes a little bit of getting used to for sure. Okay, as we look at the tangent graph, remember tangent is sine over cosine. And so as we're looking at the tangent graph, as it goes from 0 to pi over 2, the movement of the terminal side is going from horizontal upward toward vertical. So our increase, our sine is getting bigger and our cosine is getting smaller. So that's going to be getting bigger and bigger as we go, heading towards pi over 2. And it's just going to keep growing and growing and growing. Think about like if I was to take, your sine is getting bigger, right? So it's getting closer and closer to 1 as we get to pi over 2. And then our cosine is getting smaller and smaller. So if I do 1 over 1/2, say my cosine was 1/2, that's not a good one, just because it's not true. If I do root 3 over 2 over 1/2, that's the same as multiplying by 2 over 1. Which gives me root 3. If you actually take the square root of 3, you get 1 point something something something. 1.73. As I keep getting closer and closer to pi over 2, like in here, then my cosine is getting smaller, so it would be a decimal, and my sine is getting closer and closer to 1, so that I do like 0.999 divided by 0.001, that gives me 999. So my graph of the tangent is going to be way up high now as we're looking at that. So at pi over 2, we have an asymptote. So this is going to get closer and closer to that line, and it's going to keep going higher, but it never actually hits it. It just gets closer and closer to it. And the reason it'll never hit it is because if I have the tangent of pi over 2, that gives me sine, which is 1, over 0. Can I do 1 divided by 0? That doesn't work. It gives me an undefined value. That's where my asymptote comes in. It gets closer and closer to pi over 2, but never actually touches it. On the other side, if I'm going this direction, from horizontal, and this is kind of where I'm going back towards negative pi over 2, if I'm going downward, it's getting more and more negative, and for the sine, and the cosine is getting closer and closer to 0. So I'm dividing by a smaller and smaller number, or a number that's closer and closer to 0. And my sine is getting larger and larger, so it's going to have the same effect here. It's going to be getting more and more negative. And again, with negative pi over 2, my sine would be negative 1, and my cosine would be 0. Can't do that, so it gives me an asymptote at negative pi over 2. So what I'm left with is this graph that comes in between negative pi over 2 and pi over 2. Never touches them. So that's my period. It's going from negative pi over 2 to 0, so that's a total distance of pi over 2. And then it goes from 0 to pi over 2, which is another distance of pi over 2. If I add those two together, I get pi. So that's my period for the tangent. Now, just like last year we did basic transformations of a lot of functions in pre-calc, we can do those same basic transformations of the sine, cosine, and tangent functions. So we can do transformations such as shifting and stretching that we previously learned, and we can just apply those to trig graphs. Vertical stretch, that's where I multiply the cosine, sine, or tangent function by a number greater than 1. So that would be like 4 times the cosine of t. Could be 3 times the cosine of t. If I'm doing a vertical compression, it's going to be a number smaller than 1, like 1/4 times the cosine of t. What my vertical stretch is going to do is, if I'm looking at my graph, this is my original graph of the cosine of x. If I put in 4 cosine x, you see what it does? It takes my height, or what's called the amplitude, and raises it up higher. So it's still following the same patterns. My zero's still hitting the same spots, but now at 0, when x is 0, instead of being at 0, 1, it's going to be at 0, 4. It got 4 times as tall. Who would imagine that? You do 4 times the cosine, it gets 4 times as tall. Give me a prediction for 1/4 of the cosine. Yeah, it's going to be 1/4 as tall as the original was. And so we come across something that just seems to make sense to me. So vertical stretch is when we multiply by a number greater than 1. It stretches it out vertically, makes it longer. Vertical compression pushes it down closer to the x-axis, and it makes it smaller. Reflection, that's when we multiply by a negative number. So if I was to do a negative cosine of x, you'll see what it does in the graph. Maybe. I don't like that color. Why are we doing the same color? That's better. Negative cosine of x just flips it over the x-axis. Instead of being at 0, 1, it's now at 0, negative 1. Vertical shift, that's where we would add or subtract from the end of the trig function. So that would be like adding doing cosine of x plus 5. And that's just going to pick my original function up and move it up 5 units. Notice this was at 0, 1. It's now at 0, 6. And move this entire thing up 5 units. So those are some of our more basic trig shifts. All right, let's run through some example problems. What is the y-intercept of the graph of f of t equals sine of t? So the y-intercept is when x is 0. So when x is 0, what is sine? Sine is 1. That's all you have to do for that one. In exercises 20 to 33, find all exact t values for which the given statement is true. Tangent of t equals 0. So if I look at my tangent function, we go tangent of x. When is it 0? Well, I know that my period for the tangent function is pi, and I see that it's at 0 at 0. So the tangent of t equals 0 at 0 plus and minus pi. So every pi we are going to be at 0, 2 pi, 3 pi, 0, negative pi, negative 2 pi, and negative 3 pi. When is the sine of t equal to root 2 over 2? So our first spot that it's equal to root 2 over 2 is at pi over 4. And then it's also going to be plus and minus, this should have been k pi, by the way, 2k pi. But that's not our only one. It's also going to be at negative pi over 4 plus and minus 2k pi. When we look at the graph, it's easy to tell when it's going to be just one of those and when it's going to be two. So if you remember the first example, there was only one spot and then it was plus and minus 2k pi. If I look at sine of x, and then I look at when x equals, and we'll type pi, pi, divided by 4. You see it's at this spot. And then I can do x equals pi over 4, pi over 4. Then I'll do plus 2 pi. And you can see that again, I'm at this spot. Same exact spot, 0.707, which is root 2 over 2, right? So that's saying that I can do it for any 2 pi x. Desmos doesn't like when you put the x in there, okay? But I'm still missing this spot here, where it would be 0.707, whenever I get down to it. And so I would be missing that spot there. That's why I need to take the negative pi over 4 into account, because that's going to be taking these ones into consideration. Like if I do x equals negative pi over 4. Wait, that's not true, because it's my sine, so it's going to be the top side, which is going to be 3 pi over 4. You just need to check your unit circle. If I just go back and check my unit circle, When is it root 2 over 2? 3 pi over 4. So I was just kind of doing it off of memory there, and it wasn't very good. But it's going to be 3 pi over 4. I think that mistake was Donald's. I'm not going to blame Gloria or Gloriana anymore. But if we look at 3 pi over 4 on our graph, that's here. So that's about it for that one. List of transformations to change the graph of f into the graph of g. State the domain and range of g. So remember the domain and range of the cosine function. The domain is all real numbers, and the range is -1 to 1. The domain and range of cosine of t minus 2 means that I move my range down 2. So this is a vertical shift down 2 because of the minus 2 on the end, which means that instead of going from -1 to 1, I subtract 2 from both of those. It goes from -3 to -1. That's my range. Domain stays all real numbers. If I look at this one, sine, the domain is all real numbers, and the range of the original sine is from -1 to 1. Now I'm multiplying by 3. It's actually a -3, but the negative isn't going to matter here, and I'll show you why. It was originally -1 to 1. If I multiply by a -3, that becomes a +3 and a -3. And my -3 has to come first. So it just ends up as -3 to 3, which would be the same as multiplying by a +3. If I want to check that, I can just go right back into my Desmos. Get rid of all this crap. Do -3 sine of x. If I look at my bottom number is -3. Never goes any lower than -3. My top number is +3. Never goes any higher than +3. So that's about it for the type of problems I'm going to give you on this. I want you to try to do these problems on your own. Always, as always, you can come to the Google Meet if you need help. All right, it was a long lesson today. I apologize for that, but wanted to get through it. All right, guys.